Hi everyone. So I'm going to just walk through some alternative ways to represent text. So in the last video, we looked at using the multinomial naive Bayes with the bag of words representation. And in that representation, you create a vocabulary, and then you turn each document that you want to classify into a list of numbers that represents how many times each word in that vocabulary occurred in the document. So that's a basic way of representing text. It's the most kind of tried and true. But there are some tweaks to that and some different ways of looking at it. And I will ask you to take a look at that in your assignment. Take a look at some of these alternate ways of representing text in your assignment. None of the ones we're going to look at here are very smart ways to represent text. Some of them bring in a little bit more linguistic knowledge than others, but in most cases they still, at root, they're still just counting the occurrences of things and then we're going to base our classifications on that. So if you look at section 2 of the handout, the first one it says is use a set instead of a bag of words. This actually has even less information in it than the bag of words model does. Let me give you an example. So if I, let me give you, oops, okay, let's zoom that out. We don't need the words to be quite that big. Okay, so let's say document 1 is, hi there, Sam. How are you? Something like that, right? And the second one is, hi, Sam. Just saying hi. Signed, Sam. Okay, so we got two documents. Okay, those are our two documents there. Then we've got our vocabulary. So the vocabulary here would be the word hi, there, Sam. Usually we force everything to lowercase or keep everything in one case. How are you? And then the next document has hi and Sam already. Just saying. So that's, I think that's our vocabulary. So I just went through each document and made a list of all the unique words. So then document 1, if this is bag of words, document 1 has one occurrence of hi, one occurrence of there, one occurrence of Sam, one of how, one of are, and one of you, and then 0 of these words. So that's your representation for document 1. Document 2 has hi in it, does not have there in it, has Sam in it twice, has how in it 0 times, are in it 0 times, 0, and one occurrence of just and one occurrence of saying. So if that was our full corpus, this is what it would look like. We would have a vocabulary, and then each of our bag of words would look like that. If we were going to do set of words, okay, here we are. Okay, set of words would look exactly the same, except instead of keeping track of how many times each word occurs, it's instead going to keep track of just whether the word's in the document or not. Okay, so this is bag of words. And this is another representation called set of words. Okay, so there's actually less information in this representation than there is in this one. But sometimes it can do quite well anyway, and it's with a simpler representation. So this one over here is, just ignore that. That's somebody replying in our Teams system. Let me just disable that. Quit. Okay. So over here, this one uses multinomial. I'm going to run out of tablet here. NB. This one over here uses a different representation called Bernoulli NB. So this uses the multinomial distribution. When you're using set of words, you have to switch to another distribution called Bernoulli, and the object in sklearn is called multinomial NB here, and it's called Bernoulli NB here. So set of words is very similar to bag of words. It's just a 1 for each word that occurs in the document versus the count. And if you look in the code, there's actually a set of words. Where are we? There's the bag of words method, and then there's the set of words method as well, and they work exactly the same way. It's just that this one is going to count, uses a dictionary to count the number of times each word occurs. This one uses a dictionary, and if it finds a word, it just sets the dictionary entry for that word to be 1. So that's a simple alternate representation that you could try out. Now, in terms of getting smarter, bag of stems is a good thing to try. So what's a stem? Let's go over here. So let's say you have, let me go back here to here. So, oops, there we are. Okay, so let's say you have words like, let's just use spam, okay? You've also got spamming, spammed, spammable, spam-like. You know, there's lots of different words you can form off of this same root spam. And they're related in meaning, right? Spam and spamming and spammed and spammable and so on. So there's often lots of different forms, lots of different morphological forms of words that essentially share the same root or meaning, or in the terms of what we're using here, they share the same stem. So spam is the stem, and there's a bunch of different forms of that stem, but they all kind of have a meaning in common. So you might sometimes, under certain circumstances, get better performance by removing suffixes and converting all of these forms to the same stem. So if a document contained, you know, 1 occurrence of spam and 3 occurrences of spammed, you would stem all those words and get them all down to just the root of spam, and then it would contain 4 occurrences of the stem spam. So you go from a, and that may be a truer representation of how much this document is talking about spam, because it's all of these are different ways to talk about spam, right? So so the stem here of spam, if you count the number of occurrences of the stem, so you go through and each word you strip off its suffixes and convert it to its stem, and then count those, you'll end up with a smaller set of words. So it'll be more, instead of 50,000 words, you might end up with 20,000 words when you get rid of all of the suffixes and go down to the stems. So it gives you a much more manageable set of vocabulary to deal with. So you would do this when you create your vocabulary. You would stem all the words and then create a vocabulary of stems, and then go through and do bag of words or set of words on the stems. Sometimes the stems don't look like, don't actually look like any actual English word. So let me give you another example here. This is the example I think I used in the text. Was fracture, fracturing, fractured. I don't know. Let's do fracturable. Okay, so there's 4 words that contain the same stem, fracture. The actual morphological stem, if you were going to be technical about it, is really fracture with an E on it, but that E doesn't appear in 2 of those stems. So a stemmer might actually cut off, whoops, go back to my, there we go. A stemmer might actually cut off the E like this. So you would end up with the actual stem. Stem over here is the word, whoopsie. Let me try that again. The stem over here is the word spam, which looks like an English word. The stem over here is the word fracture without the E. So the stems sometimes don't correspond exactly to correctly spelled English words, but again, that's going to capture a lot of the common meanings of the common meaning that these words share. So that's another option, is a bag of stems. So you could do stemming in a number of ways. You could create your own little algorithm that just removes trailing suffixes, E, ES, S, ED, ING, ER, etc. You could even remove prefixes as well, which most stemming algorithms don't do. So what's the example up here? Refractured. You would take away the ED and the RE and end up with just fracture without the E on it. So that would reduce them all to a single stem. There are also stemming algorithms out there that you can use, and maybe we'll talk about that in the live class. We'll talk about some of the options that are out there for automatic stemmers There's this NLPTK, it's NLTK, the Natural Language Toolkit, which I think you can import. But there's, it's already in Anaconda, but there are some, when you want to do stemming and stuff like that, you have to actually load some stuff that's not already in here, some resources that are not already in here. All right. We'll look at that in the live class. I'll put that on the list of things to look at in the live class. So stemming. Here's another representation that's often used. Instead of a bag or a set, you use this TFIDF. I'll let you guys look that up. But you compute the term frequency and multiply it by the inverse document frequency. Or another way to put it is you divide by the document frequency. So you count the number of times the words appears in the document, divide it by the number of words in the document. So you're going to get some measure of how frequent the word you're interested in is in the document. And then you look at the number of documents in the corpus divided by the number of documents with that term in it, and you multiply it by that. So the idea is that if it's a very rare word, what this does is it bumps up its count. So if this is a rare word, it doesn't appear in very many documents, but it does appear in your document, then it's given a higher count. It's given a higher number, and so its importance goes up. So maybe the word war doesn't appear very often in documents about politics, doesn't appear very often at all, but it's a really good predictor. So this boosts its frequency when it does appear in a document, boosts its measure. So that's called TF-IDF. And you can use it with stems. You could use it with words, or you could use it with stems and just use multinomial NB on it. The other thing you can do, a couple other things you can do, bag of Engrams. So an engram is a sequence of n items that appear together. So if you use just bag of words here, you're going to get the word an, the word engram, the word is, and so on. But if you decide you want to use 2 grams, then this will contain an engram. Engram is a sequence. So what it does is it preserves some of the word ordering, and it lets you capture phrases like Donald Trump or inverse document frequency. If you're looking at 3 grams, you would take lists of 3 words. And all of these things get added to the representation. So one of the things it does is it explodes the size of your representation. You go from maybe 10,000 words to hundreds of thousands of words, hundreds of thousands of engrams. So you got to watch out for that. But it can add features that would actually help you in classification. Okay, so you preserve some of the word ordering. You're going to increase the number of features. But what you could try is just adding a few engrams to your set, or you could add all the engrams and then remove the infrequent ones, which we'll look at in a second. That's another thing you can do. So all of these different representations can be combined. Stop word removal is another thing that people do a lot. So English, any language, well, most languages, but English especially, has a huge set of content words, and then a pretty small set of words that are just pure grammar. So of prepositions, articles, things like that don't really carry a whole lot of meaning. You might balk at that a little bit, but the word the doesn't really carry a lot of meaning, or maybe even doesn't carry any meaning at all, as evidenced by languages like Russian that don't really have them. That's why that gives people who speak with a Russian accent a particular feel to the way they speak, is they tend to omit the determiners because they don't have them in the language that they grew up speaking. So you don't really need a lot of these grammatical words. They're just there. They're there to smooth out the grammar and to make it, maybe to make it clear kind of the subtle sense of what's being said. You can find lists of these words online. If you just Google English stop words, you'll find them. And you can also combine it with some stemming, and it's going to reduce the number of features in your set by a fair bit, and it might give you a little bit of a boost. So removing stop words is another option. And then finally, this is really the only other one that's really going to be reachable for us, removing frequent and infrequent words. So that's another common practice. Removing infrequent words, like there might be words, if you've got 50,000 words in your corpus, if you got a vocabulary of 50,000 words, it's possible that 10,000 of them only ever appear one time. They're probably not going to be super useful for your classification task. So if you just cut off any word that only appears once, you're going to speed things up quite a lot by going from, say, 50,000 to 40,000 features. If you set that bar even higher, like at 2 or 3 words, you're going to cut off that tail even more and go down to a much smaller set of features. Okay? So yeah, here's an example. You might have 16,000 words, but 6,000 of them only appear once. So removing those words is going to speed up the classification. But you might lose valuable info in the process. Okay? Removing frequent words doesn't remove as many words, because frequent words are, there aren't that many of them in the Canvas, in any corpus. But if if a word is so frequent that it appears in every document, like this kind of interacts with stop words. Like the word "the" is pretty much going to appear in any document of any length. It's not going to help you very much classifying, probably. So if you remove very frequent words like that, it might make the classification task a little bit easier. Okay, so in the assignment, as usual, I'm going to ask you to try different versions of text classification, and this gives you some ideas for what you can do. So you can do bag instead of set. You can do term frequency, TFIF, and you can do stemming, Engrams, stop word removal. Lots of options to try and make, and removing infrequent and frequent words. Lots of options both to speed things up and to maybe help boost the accuracy a little bit. And then you could also do more sophisticated NLP, but I don't advise trying that. And as it turns out, the statistical methods tend to still beat the more sophisticated stuff anyway. So some exercises to try, and this is stuff that can directly help you in the assignment. Make a new version of Create Vocab List that removes stop words, right? There's a list of stop words in the week 1 exercise solutions, I believe, or it might be the week 2 or week 3 exercise solutions. Try those. Try that. See if you can see any performance difference for doing that. And you can also, once you've written it, you can try it in your own, in your assignment as well. So you would do this again in creating vocabulary list. You would remove the stop words there to get a shorter vocabulary, and then that would lead to shorter vectors. You could just give that vocabulary list a bag of words. It'll ignore any word that's not in the vocabulary list. So that's a pretty easy one to do. The other thing you could do is some stemming. So do some simple stemming. You can make it up yourself, or you can find some stemming stuff online. So try that, or try combining them. Now when you stem, you're going to have to stem when you do the text parsing. So the minute that's the best place to do it. If you're using my code, text parse takes a string and turns it into a list of words. If you stem there, then you'll be dealing with stems from that point on. When you create the vocabulary list and the Word documents, the bag of words representations, everything will be stemmed if you're stemming it in text parse. Okay. And then, even try some of the other stuff, but there's a couple things you can try to work on. Just give that a try. And again, this will help you. This gets you going on potential things that you can do for the assignment. Okay, so that's it for this video. We got one more on a new way of measuring performance of an algorithm that we're going to need for this assignment. So that'll come in the next video, and then what I'll do is in the live class, we'll take up some of these exercises and we'll take a look at the assignment. There's a bunch of code that goes with the assignment as well. So we'll take a look at that all together. Okay.